So, we've been talking about right triangles in trigonometry. Today we're going to take a look at triangles that don't have a right angle, or called oblique triangles. All triangles have 6 pieces to them, 3 angles and 3 sides. If we know any 3 out of those 6 pieces, as long as it's not all 3 angles, so that's one of the conditions, is one of the 3 pieces we know has to be one of the sides. But as long as then if we have at least one side and we have a total of 3 pieces of the triangle, we can find all of the other pieces, whether it's a right triangle or not. Let's label this angles A, B, and C. So now the sides are labeled by the angle that's opposite them. So this would be side A, side B, side C here. The relationship that exists, now remember we said that the largest side is opposite the largest angle, and the smallest side is opposite or across from the smallest angle. And that's true, but it's not just a direct. If the angle's twice as big, the opposite side isn't twice as big. The relationship goes with the sine of the angle, which brings us to something called the law of sines. The law of sines states that the ratio between the length of a side and the sine of its opposite angle is a constant within a single triangle. And some books will put the sine on top and the length of the side on bottom, and some books do it the other way. I always like to put the length of the side on top. So it'd be the length of side A over the sine of angle A is a constant for the triangle. So that would mean the length of side B over the sine of angle B is the same ratio. And in fact, the length of side C over the sine of angle C is also the same ratio. So let's take a look at an example of this. Let's do a triangle with some numbers in it. So let's start out here with angle of 81 degrees and over here 72 degrees. And I'm going to have a side over here of 19 feet. Now for law of sines, I must have an angle and its opposite side. If I don't have that, I can't use the law of sines. Well, fortunately, anytime I have 2 of the angles of a triangle, the third one's pretty easy to find, isn't it? So anytime I have 2 angles and at least one side, I can use the law of sines, period, no matter what. Because here this third angle is going to be found by doing what? Yeah, 180 minus 81 minus 72 is 27 degrees. So we have all 3 angles now. Next we can find the missing sides. Now we have one side here which is the 19 feet. What is its opposite angle? 81. So it's going to be 19 over the sine of 81 degrees. Now we can pick either of the other sides that we want to do. I'm going to pick side B for now. What's its opposite angle? 27. So that'd be over the sine of 27 degrees. So this calculation, I'm going to cross multiply and divide 19 times the sine of 27 and divided by the sine of 81. So 19 times sine 27. Make sure you close the parentheses. Divided by the sine of 81. I'm going to close them up again. Equals 8.733. So that is 8.733 feet. 8.73 we'll round it to. Does that make sense? Well, yeah, the 27 is considerably smaller than 81 degrees, so it makes sense that that side would be considerably smaller than the other side. Well, now we're going to go back to the 19 over 81 degrees again. Over sine of 81 degrees. Equals, we still need to find side C. That'll be over the angle of 72, so sine of 72 degrees. And once again, it will be cross multiply and divide. 19 times sine of 72 divided by sine of 81. Which gives us 18.29 feet. Now, 72 degrees is smaller than 81 degrees, so it makes sense that the length of this side would be smaller than 19. Bless you. 72 is not a lot smaller than 81, so it does also make sense that they're close to the same size. So anytime we have two angles on one side, we can use the law of sines. If we have two sides and one angle, it can be a little more complicated. I'm going to show you this first case where it's not so complicated. Let's say this angle here is 53 degrees. We'll call this over here 38 feet and 27 feet. So of course this is A, B, and C for the sides. First question, do I have an angle on its opposite side? Sure do. So I have 38 over the sine of 53 degrees. Then I have 27 over the sine of angle B. When I am looking for an angle, there's going to be an extra step here. So here's what I'm looking for. I'm going to still cross multiply and divide. Sine of 53, again making sure I close the parentheses, times 27 divided by 38. Gives us 0.5675 if I round it. But that is not the angle, that is the sine of the angle. The angle itself is going to be the inverse sine of that number. So in order to keep from writing it down and rounding it off, I'm going to do it right in the calculator. Second sine, and then second answer. Telling the calculator to take the inverse sine of that previous answer. Close my parentheses, and I get 34.57 degrees. It makes sense that this angle would be smaller than this one because this side is smaller than that one. Smaller angle, opposite smaller side. Smaller side, opposite smaller angle. However you want to look at it. Now to find the third angle, what do? Well, 53 and 34.57 make 87.57, makes this 92.43 degrees. I just subtracted from 180. And now, of course, you can find this length by using the law of sines again. I'm going to trust that you guys can handle that. What we do have to worry about when we have two sides and an angle is a case like this. Let's say the angle A is 31 degrees, side A is 14 feet, and side B is 30 feet. If we try to draw a triangle for this, we're going to run into a problem. Let me try to draw a little bit more accurate than that. So that's my 31 degrees for angle A. Side A would be over here at 14 feet. This is angle B and C. This is my 30 feet for side little b. If I put my 14 over the sine of 31 degrees equals 30 over the sine of b. Once again, I'll cross multiply and divide. Sine of 31 times 30 divided by 14. 1.1037. What's wrong there? You try to do an inverse sine, but I'm going to save you the trouble. What's wrong with this? Sine can never be larger than 1. If you try to do an inverse sine here, it'd give you an error. What this is saying is this is not a triangle. If this angle here is 31 degrees and this side is 30 feet, 14 feet is not enough to reach back down to this side. So this cannot form a triangle. It's not solvable because it's not a triangle. Exactly. Now there's a second possibility that can happen here. When you're given two sides and one angle, if the side that is opposite the angle is the shorter of the two sides, this sometimes pops up where it doesn't reach down, it doesn't form a triangle. But even if it does reach, there's a problem. Let's say that was, let's keep A at 31 degrees, let's keep little b at 30 feet, and let's put little a now at 20 feet. 20 feet would be definitely long enough to reach down to the other side. But here's the issue you run into. So this is 31 degrees here. This is 30 feet. When you get to here, however, does that 20 feet for side A go this way? Or does it go this way? It can work either way. So what we need to know here somehow is if this angle B is either acute, like this one, or obtuse. What if it's obtuse? So let's actually draw a picture. Let's say we're given a picture with the problem. It looks like this. This is 31 degrees, 30 feet, 20 feet. So we go ahead and set this up. 20 over the sine of 31 degrees equals 30 over the sine of B. Cross multiply and divide. Sine of 31, close the parentheses, times 30 divided by 20. We're still less than 1, so we know it actually makes a sine. So the sine of B equals 0.7726. We do our inverse sine, second answer. We get 50.58. Does this angle look like it's 50.58 degrees? No. Remember back to our unit circle? If you have this angle, that sine of being 0.772, that's the sine. Is there another spot on the unit circle where we have the same sign? Right here, right? That angle would be the same angle here, but the actual angle itself would be the supplement. So we get this inverse sine. It can be this angle, or in this case, since this is obtuse, it would be 180 minus that angle, or 129.42 degrees is what that angle actually is. So that is something to be careful of with the law of sines. If that is an obtuse angle, you'll use the law of sines, but you have to take the supplement of your result to get the actual angle there. On Monday, we will do more examples of these. Only if this is an obtuse angle that you're finding here. Then whatever angle the calculator gives you will not be correct. It'll be the supplement of that angle. Will be the correct angle. You'll either have to have a picture that clearly shows it obtuse, or they'll have to tell you that it's obtuse. So out of your books, on page 781, exercise 36-8. And also on page 784, exercise 36-9. Goes over the law of sines and solving triangles with the law of sines. Like I said, on Monday we'll do more examples, answer homework questions, maybe get to law of cosines on Monday and do a quiz. At some point in the next week, you guys are going to have a unit test coming up.